Hello students. Uh, in the previous section, we have discussed the estimating the hypothesis accuracy, and we have seen why it is very important for us to estimate our hypothesis, right? That is accuracy of our hypothesis. So in today's topic, we are going to look into the very important concept of errors. So why we are discussing about the errors? So like in our previous topic, we were talking about the accuracy, right? So accuracy and errors are vice versa, because say for any example, if you say that 90% accuracy is there, so you are given one, or you have stated a hypothesis saying that tomorrow it is going to rain. On what basis you are going to prove or support your hypothesis? You are going to, based on certain data and based on certain facts and learning, you are going to tell 90% there is a chances or probability that tomorrow rain might come. So now when you are telling 90% accuracy is there, means 10% it is not there, then what is the 10%? The 10% is your error. So now we are going to talk about this error. So what is this error? And especially we are going to define two types of error. One is called as a sample error and the other one is called as a true error. So to answer this question, we need to distinguish carefully between two notations. That is, when you are trying to answer about the errors, right? So there are two important notation of accuracy. How you are going to talk about the accuracy or equivalent, right? So the first one is called as the sample error. Now what do you mean by sample error? One is the error rate of the hypothesis over the sample of data that is available. How much of data you are having, that we call it as sample error. See, now you are going to conduct an experiment, like say for example you want to identify, or you are going to talk about or predict the average height of a students in VTU. Now if you want to predict average weight of students in the entire VTU, so now what you are doing, so you need some sample, right? So what we are doing, so you take your class strength or your college, the number of students in the college, based on that data. So say for example our college has got 100 students. Now we try to note down or collect the height of all these students, right? So we collect the height of all these students, because we don't know what is the total number of students in our entire VTU. This is our entire population, but what is there with us in hand? We have got a small sample of data of 100 records or 100 students. Now for this 100 students, now you are going to collect the data, right? And you try to identify the what you are saying, the error in that, right? So now this we call it as the sample error. So error rate of the hypothesis. So when you are saying that 90% of this 100 the data sample what you are having, now their accuracy is there, means 10% error is there. So there is a 10% error in this data, but what is the how much error is there in this? So now this is your sample, so we call it a sample error. Try to understand carefully. Error rate of our hypothesis over the sample data which is available with us, we call it as sample error. Now in the other way, the error rate of hypothesis over the entire unknown distribution D. This is unknown for us. We don't know how many students are there in the entire VTU, right? So now when you are going for an entire population, so what error you might get in this population, we call it as true error. This is the actual error. So whatever error we are getting right now, this is with respect to the sample what you are having, so we call it a sample error. But the error associated with your entire population, we call it as a true error. Clear? This is how we are going to define a sample error and a true error theoretically. So now the sample error of a hypothesis, right, with respect to some sample S. So you have got some sample S of instances drawn from X is the fraction of S that it misclassifies. So it is going to misclassify. Say for example, you you are having, like, say 50 records, right? 50 records or 50 photographs of let us say apple or an orange. Now out of these 50 records, what you are going to say, how much is misclassified? Now say that in this 45 images are being correctly classified as apple, then 5 records are misclassified as apple, right? Now you are getting now. So 5 errors are misclassified. So now when the sample error of an hypothesis is with respect to some sample s, so you are going to have some sample s, and in that, from that sample, when you are going to draw some instances, now that instances, how much percentage of that instances are being classified or misclassified? Misclassified means error. This is what we are going to call it as an error. So now mathematically, now we can define a sample error. So the sample error, which is denoted as error subscript s, this is very important. Note down, this subscript s means we are talking about sample error. So error subscript s of our hypothesis. So the sample error of hypothesis h with respect to a target function, right? We are having a target function and a data sample. Yes. So now this sample error, so now it is nothing but, so error subscript s of h is equivalent to 1 divided by n summation of all the instances belonging to your sample, right? And average, so it is the average of all difference in your target and the hypothesis. So it is a delta of f of x comma h of x. What is this f of x? Now this is the target, right? This is the learned target what you are having. This is the learned target, and h of x is your hypothesis. So now between your target and your hypothesis, that difference what you are going to get, right? So that is the average difference. Now that is our error. That's what we are telling. Suppose you wanted to get 50 as the output. 50 is your target f of x, but you predicted, your hypothesis is giving you 45. Your hypothesis is giving you 45. So now what is this difference? Difference is 5. That means there is an error of 5%. That is what it does. Excuse me. So now you are going to find the summation. So it is the average of all differences divided by n, right? Now where n is the number of examples in our excuse me, where n is the number of examples in S, and this quantity delta of f of x comma h of x is 1. Now we say that this is 1 if f of x is not equal to h of x. So if your target, see, if your target value, excuse me, if your target value, if it is equal to, so if the target is 50, now your hypothesis is telling 50, it's also giving you 50. So both are same. If both are same, then you don't have any error. So what you are telling, if this target and if our hypothesis values are not matching, then we are saying this delta of f of x comma h of x is equal to 1. That means error is there. Otherwise we are saying 0. So 0 means there is no error, both are same. So this is how mathematically we are defining what is called as a sample error. So now we will try to look into a true error. True error means we are going to entire population, unknown distribution, you don't know how much is there, right? Some population is there. Now the true error of a hypothesis is the probability that it will misclassify a randomly drawn instance from the distribution D. So now when you consider your entire population, in this population, if you take one particular sample, whether this instance is being classified properly or not. So the probability of that which misclassifies, right? So with misclassifies, we call it as a true error, because now you are considering the entire population. So now this true error. So now you are going to define true error. Now this true error is denoted by error D, subscript D. D with respect to distribution. So D means true error, S means what? Sample error. So this is the notation you have to remember. So now error D of H of hypothesis H with respect to a target function F and your entire distribution of your entire population. Now this is the probability that hypothesis H will misclassify an instance drawn at random. You are just taking one random sample and you are going to see whether this is misclassifying. What is the probability that it is misclassified? So this can be written as error of D of a hypothesis equivalent to probability for all x belonging to your distribution. How? When f of x not equal to h of x, right? When your learned target, if it is not equal to your labeled predicted hypothesis, then there is an error. If it is both are same, there is no error. So this probability of f of x not equal to h of x, so we call it as a true error. So in this particular notation, this PR means what? Denote the probability which is taken over the instance of your distribution D, right? So now what you are going to say? So now if you have got a 20 data sets, 20 sample data set you are having, now you are classifying 15 of this are being classified correctly, right? And remaining 5 is classified wrong. Then what we can say? So we can say that 25% of true error is there. If your entire population has got 20 data sets, 15 are classified correctly, but how much are misclassifying? 5 are misclassified. So what is the percentage probability of this true error? It is 25%. So 25% error means 75% is accurate. This is how both the accuracy and error goes hand in hand, right? So now what is that? What we usually wish to know. So what actually we need when we are talking about estimating the hypothesis, accuracy of our hypothesis means what? So now we wish to know that is the true error, that is error D of H of the hypothesis, right? We actually want for the true error. Sample you are having, with the sample you are learning, but when a new instance comes, you are going to take randomly from the population. That instance, how much is misclassified, right? Error D of H of hypothesis, because this is the error we can expect when applying the hypothesis to future example. With a small portion of a sample, how much error you are going to get, and when you are considering entire population, from this entire population randomly if you pick one particular instance, now what is the probability that this instance is misclassified? That's what we are going to talk about, the true error. So true error is important for us, right? So but it is very difficult to find the true error because we don't have complete population, everything lies on the sample error only. Now all we can measure however is the sample error. So this error is easy for us to measure. Why? Because we have collected some data points, some data set, some sample is there. So error, that is the sample error of hypothesis for a data sample S that we have to that we happen to have in hand, right? That is what it says that. So it is what all we can measure at the maximum. We can talk about sample error because data set is there in your hand, you can measure the sample error. Now our question is that how good an estimate of the true error is provided by the sample error. With your sample, with the help of this sample, if you are saying that there is 5% of error is coming with my model, then when you go to your entire population, at that time also whether your model is doing 5% or what. If it is with your sample it is doing 5%, and if you are when you are taking your entire population, then also it does 5% only, then your model is very good, it is very accurate. That is what our main question is: how good an estimation of a true error, this true error in entire population, is provided by your sample error, right? This is what our main question, right? To answer this question, we need to distinguish carefully between two notations of accuracy or equivalent error. So one is the error rate of hypothesis over the sample of data which is available. One is sample error, this is what you are having. The another is error rate of hypothesis over entire unknown distribution, that is our true error. So now this is what we want to do. Now to understand this, now we are trying to look into another important concept which is called as confidence interval. So with what confidence interval you are going to tell? With what confidently you are going to tell that when you go to your entire population, this is what the percentage of error I am going to have, right? Now what is this confidence interval? This confidence interval, it displays the probability that a parameter will fall between a pair of values around the mean. So between which value your mean is going to come, and how much confidence you are by observing the sample error, how much confident you are in telling that with respect to entire population your true error is going to have. So we are going to now understand this confidence interval for discrete value hypothesis. So discrete value means we are considering a discrete samples or the examples. Now suppose we wish to estimate true error for some discrete valued hypothesis H based on its observed sample error over a sample S. You are taking some example. Let us say example is you want to predict which party is going to win the election. So to do that, you don't have the total number of voting list or people of entire India, and it is highly impossible for you to go and ask each one which party you are going to vote. Maximum what you can do, you can collect some sample, right? Some sample you are going to ask. You try to have a query or try to conduct a survey with some sample, around 1000 samples, 1000 people you have asked. Now when you have asked 1000 people, there is some error, so which we are talking about sample error, right? So you take such a type of an example. Now the sample S contains n examples. So when you are going to consider one sample, let us say you are given one sample. Now in this sample you might be having 10 data sets, right? You may be having 20 values, or like say from 20 people you have collected the information. Like this, there might be some examples which you are saying n. S is a sample. In this sample you have n example which is drawn independently of one another. That means one example is not dependent on another, both are independent. Randomly you are picking, and independence of H, and with this independent, this is according with our probability distribution. It has to obey the same distribution of our entire population. Next important thing, we are assuming n greater than 30, and always it is preferable that now the how many examples you are going to consider in your sample space, yes, greater than or equal to 30, or at least 30 data samples you should have in one sample, yes, right? Now it is very clear. Now hypothesis yes commits R errors. Let us say that now your hypothesis is trying to commit R errors. There are R number of errors over n examples, right? Over n sample examples. Suppose say that you have collected 10 data examples. Now when you are going to classifying 10, 8 you have classified correctly and 2 is misclassified. So what is this error? Error is 2. This is what we are telling, R errors. So hypothesis yes commits R error over n examples. Then how do we calculate the sample error? So sample error of H is equal to how do you calculate R? How many errors you got? So here out of 10, 8 is classified correct, 2 is misclassified, then what will be your error? So 2, how much misclassification has happened? 2 divided by how many example you are taking? 10. So 2 divided by 10 is your sample error. Now this is how you are going to calculate sample error. Now under these conditions, statistically theory. So now we are going to take help of statistics and we try to make following assertions. Right, now we try to follow or make some assertion. What is that? By taking statistic theory, first one, given no other information. So we are only given this above information. When no other information is available, then the most probable value of true error is equal to sample error. Now what we are telling, with this sample, what error you identified R by N, now we are going to say that when you consider the entire population true error, when you identify the true error, then that true error also will be almost equal to your sample error only, right? Probable value of error D is what? This is true error. So what we are telling, true error is almost same as your sample error. Next, second point, with approximately 95% probability, right? 95% of probability, what we are going to tell, the true error, that is with respect to your entire population. Now this true error lies in the interval. So it lies in the interval sample error plus or minus 1.96 into square root of sample error multiplied with 1 minus of sample error divided by n. Now this is our equation. Okay, it will be more clear when we take up an example. So what we are going to say, so 95% means this 95% probability is your confidence interval. Now you are 95% confidence that the true error with respect to your entire population, always it lies in the interval. It lies between this. What is that interval? Sample error plus or minus 1.96 into square root of sample error times 1 minus sample error divided by n. Right? So this is how we are going to define the confidence interval. Now let us take an example and we'll see. Now suppose say that you take a data sample S. Now how many data points are there in this sample S? You have got 40 examples. So n is equal to 40 examples. And your hypothesis commits R errors. How many errors? 12 errors. Out of 40, 12 are misclassified. So now how do you calculate your sample error? So sample error is equal to what? R divided by n. Right, that equation. What is the errors? How much errors you have misclassified? 12 divided by how many examples? 40 are there. So 12 by 40 is 0.30 is your sample error. Now given no other information, now what we want to tell is that the true error, right, this true error in your entire population which is observed is the observed sample error 0.30. 0.30 is your sample error. Now what we are telling is that with the help of this statistics or the confidence interval, now what we are telling, the true error, this true error lies between, or it is almost equal to your sample error only. But we don't expect this to be perfect estimation of the true error. So it is not a perfect estimator. That means this sample error 0.30, when you are saying true error also is not same as this. There will be some difference. That is why here we are saying plus or minus. It can be more than 0.30 or it can be less than. But what is that range? Right? That is what interval what we are going to tell. We have to calculate that particular interval. Right? So now we'll see. Now we will repeat the same experiment. Now you are going to have a second sample. One sample you collected here, right? With this sample which has got 40 examples, you got 12 errors and you calculated sample error. Now you take another sample S dash. Now this S dash also has got 40 examples. which is newly randomly drawn examples. Already you did for S, now you are going to do for S dash, right? Another new sample. Now we might expect this sample error. Now when you look for this new sample S dash, what might be your sample error? It might be 0.3 or little bit slightly up or down, right? So this new sample error S dash for H, it can vary slightly from the previous value of 0.3. Now we expect a difference. There is slight difference. Why there is a slight difference? Randomly you are selecting some samples between S and S dash. So there will be some differences will be there. Now like this, if we repeat this experiment over and over and over. So first time you took one sample S1, right? It has got 40 example. You calculated sample error. Next you take another sample S2. Again that also has got 40 example. You calculate sample error. Like this, if you keep on repeating this experiment, every time, each time drawing a new sample S which contains 40 new example, now we could find that approximately 95% of your experiment, when you are going to conduct like this, 95% time the calculated interval would contain the true error. Now when you do this experiment for more and more samples, 95% time what error you are going to get, that will be the same as your true error. That is what you are going to estimate now. See, we told it is very difficult for us to find the true error because we don't have the population. We don't have how many data are there in the population. But what is there? Sample is there. Now when you do this for sample error S1, S2, S3, taking different samples, and when you keep on calculating the error, now it is estimated that 95% time what error you are getting here, almost it will be same as your true error. So for this we call this interval as 95% confidence interval estimate for error, right? So now how we are going to calculate this for 95% confidence, right, for this example? Now with the equation. So now what was our equation? So we told that the true error lies between 95%. See this equation we are going to calculate here. This equation for how much percentage of confidence interval? 95%. So now you have got a sample error. So now how we are telling? So sample error, what is your sample error? What you calculated? 0.3, right? So 0.3 plus or minus, right, 1.96 multiplied with square root of sample error, which is 0.3 into 1 minus of sample error, which is 0.3 divided by n. What is n? 40. So your true error will lie in this 95% times confidence interval. So now when you calculate this, so you will get 0.3 plus or minus, right? So here you have got 1.96. Later we will see why this 1.96, right? Square root of. So now when you, so this is 0.3 into 1 minus of 0.3. 1 minus 0.3 is 0.7. Now 0.7 into 0.3. So you are going to get 0.00525. You can calculate by yourself. It is very simple calculations. Now square root of 0.005525. So you are going to get 0.072. Square root of that. So now what you are having? So now your equation becomes 0.3 plus or minus. So how much you got? 1.96 into, so what is this, the final square root value into, see this one, 0.072, right? So now this further simplified to 0.3 plus or minus 1.96 into 0.072 is 0.42. Now what we are going to tell is that your true error, so true error, right, 95 percentage, with respect to 95% confidence interval, true error will be always sample error 0.3 plus, see, plus or minus plus 0.4. so how much it can be? This one, 0.3 plus 0.42, it can be 0.73, or it can be subtract 0.3 minus 0.4, right? So 0.12. So between 0.12 to 0.73 will be your true error. 95% of time it lies between this. That is what this confidence interval tells. Clear? I think it is very clear. Or with this, how with that equation, how we have calculated our confidence interval. Now we will see why we are telling this 95% and why in this particular equation you got here 1.96. So now this, in this expression for this 95% confidence interval, now it can be generalized to any confidence level. See, you can tell with respect to 80% confidence what will is your true error, or 60% confidence what is your true error. How you can generalize it to any confidence interval? Because when it is 95% confidence interval, you are going to multiply it with a constant 1.96, right? So in this expression we are multiplying here 1.96. Why 1.96? Because we are having 95% confidence. If it is 80%, this value will change. If it is 60%, value will change. If it is 98%, value will change. How we are going to get this value? So this value can be obtained, that is what we call critical value. It can be obtained with one table. So that value we call it as a Zn, critical value Zn, which is used to calculate our n% confidence interval. In general, we can generalize this equation as sample. The true error always lies between sample error h plus or minus Zn, right? If you are talking about 95% confidence interval, this Zn value will be 1.96. If you are going to calculate for 98%, the value change. From where you get this value? So there is a critical value table in statistics textbooks or in your machine learning. At the end, a table is given. With the help of that table, we can try to get that value multiplied with square root of same sample error times 1 minus sample error divided by n, right? So now if you look here, now this is your confidence. So this is this table. This is the value of Z score for two-sided n% confidence interval. So now you can see in this particular table, when you are talking about 95% confidence, what is the constant value you have taken? 1.96. If you are talking about 80%, it becomes 1.28. Based on which confidence intervals, now this value you are going to have. Clear? Now if you take this example, now this is a normal distribution graph where this green color, now this entire region, this is our 80% confidence. Now 80% of your data lies here. That means your true error lies between this. When you are considering 80%, now what is your Z value? Z value is 0.128. So 80%. Now this portion we call it as a tail region. Now when you are taking here tail region, 80% means 0.8. So 0.8, this is where your region covers. Now this will be, so 0.1 and 0.1. So this is 0.1 and 0.1. So when you add up, this becomes your 100%. Right? So now this is your 90%. So we say that 90% confidence. So when you are saying 90% confidence, with the 90%, when you are saying your confidence interval, so your true error lies between here and here. See, this will be plus, this is positive and this is negative. That is why in your equation you have got plus or minus here. Either it can be greater sometimes or it can be less, because it is an estimation. So when you say 90%, then what will be your constant multiplier? It should be 1.63. Clear? Now this is our what is called as the confidence interval. So thus, just as we could calculate 95% confidence interval for the previous example what we have calculated, so that is 0.30 sample error plus or minus 1.96 multiplied with 0.07, right? Previously we have calculated that. So where R was 12, error was 12 and N was 40. Now we can calculate it for 68%. Now if you want to calculate instead of 95%, if you want to calculate for 68%, now what changes you have to do in your equation? Everything will be the same. Sample error is also same, plus or minus. Instead of 1.96, because you look into this table, 1.96 was 95%. Now if you want to calculate for 68%, now from this table for 68%, what is this interval or the constant value Zn, critical value, we call it is 1. So you have to multiply it with 1 here. See here 1 is there. 1 into 0.07. For 95%, 1.96. If it is for 98%, 2.33. That is going to change. So note that it makes us an intuitive sense that 68% confidence interval so is smaller than 95% confidence interval, because when you go for 68%, your area becomes very less and less. You can see here 80% means this. When you go for 68% means still lesser area you are going to have, right? So 68% confidence interval is smaller than 95% confidence interval, because we have reduced the probability with which we demand that your true error falls in that particular interval. When you reduce your probability, so then you are saying that your true error does not fall in that particular confidence interval, right? Now this is about your the sample error, true error and confidence interval. So in the next topic we will look into some of the basics of our sampling theory. So you have to understand some of the definitions which comes in our sampling theory. What is mean, what is variance, what is binomial distribution. So those basics of our sampling theory, now we will try to look into these definitions in our next topic. Clear? So you just go through these things carefully. That is sample error and the true error. So definitions will be asked in the examinations. So thank you for watching. Have a nice day.